Next up, from Montclair State University, Dr. Mary Lou West. KC2 NMC. Please give her a warm welcome.
How do you do? Dr. Mary Lou West taught me everything I know about physics. She was my undergraduate physics advisor and professor. So I'm very happy that she is here today presenting this.
Diego Sanchez has been my student for a couple of years in a research project dealing with these large-scale TIDs. So we're kind of related to Veronica.
Oops. Would you feel more comfortable with the regular one?
So what we've been doing is looking for these LSTIDs with aggregated ham radio spots. So I'm just so pleased to see all the ham radio people who have been communicating with each other and putting little spots on my graphs here. Okay, so cool. Thank you. So as an outline here, tell you a little bit about the LSTIDs, the characteristics of 2017. So we first, most of the data here is talking about 2017, but lately I've gone on and done the next 4 years as well. So there's some data about them. We really want to find out what drives these things. What makes the bottom of the ionosphere going from flat to rippled? All right, I'll give you an example from the atmosphere below. That's the Tonga explosion of the volcano, so cool. And then an example from above, the Aurora electrojet. And we will compare the possible drivers, and we just found a couple more. So my plea to you is, if you have another driver you'd like considered, tell me, and we'll work through that one as well. And then we have some tentative conclusions. And the biggest conclusion is this new set of data is really powerful, and it's wonderful, and big data is just so cool. All right, so here's what happens with traveling ionospheric disturbances. When the bottom, the reflective layer, whatever the reflective layer for the frequency is for that you're using, when it ripples, then it gets places where something that had come down at this place now comes down over there, and so things change on the ground. So in 2017, we can say that there were 102 days out of the 365 days which had TIDs on them, definite TIDs. There are a lot of other days where, who knows, it was all smushy, and a lot of days where it was just flat. All right, so that's 28% of the days. So in the other several years that I've done now, it's generally 30 or 35% of the days have one of these disturbances in it. Okay. We looked mostly at 14 megahertz, but also did some work at 7 megahertz. Then realized that 7 megahertz was useless, and so didn't do that in the other years. Okay. Some is at night, most is in the daytime. The period that we're looking for is between 1 and 4 hours in length. The MS TIDs are shorter than an hour, so often like 30 minutes, something of that sort. That's the difference between them. The durations are certainly at 14 megahertz, generally 5 to 9 hours during a day. So once one of those things gets set up, it keeps on going. So, and there's a large difference in the range. That is, when we see this oscillation, I'll show you a picture in a minute, we also measure the minimum and the maximum range that it has, and that's just in sections of 100 kilometers at a time, and that is often several 300, 400, 500 kilometers in difference where the bottom of the skip layer is from place to place or from time to time. That max to min is indeed seasonal, which you would expect. If the sun shines more in the summer, then it's going to drive the bottom of the ionosphere closer to the Earth, and in the winter it shines less, and so it goes back up. But that's an interesting seasonal variation that we're going to look at next, another time. So here we have something about what we did. We have two different people looking at this, two sets of eyes. We both looked in detail at 2017 quite separately, and then we talked about it. For 95% of the time days, we did agree on what had happened. The other 5%, we had to have a discussion. And then either chose his view or my view and wrote it down. But we had to convince each other. So you see, I don't have no pointer. All right, so the top one here is what I saw at 14 megahertz, and the bottom one here is what he saw at 7 megahertz on the same day. And you can see it goes over and goes up and down, same thing. Quite a noticeable difference. Now what you have plotted here is time UTC. This is from 12 to 24 daytime, and what's going vertically is the distance, the Earth distance, great circle difference between the one person who's transmitting and the one person who is receiving. So on the left you see a calm, flat day. The bottom of the blue layer there is flat, pretty much, and then on the this one, we see something that has a variation, a sinusoidal variation, but this one also has a contest. Can you see where the contest begins? Golly, people jumped on it right at the moment when it began. That was pretty cool. Here's one in which there was a solar flare during the day, and we see over here, things were going along, and then, oh my God, it all went black. And stayed that way for an hour or so, and then slowly squidged its way back to being normal. And here you see it in the data from 7 megahertz. As to climatology, we counted up in 2 different ways, and they turned out to be equivalent. So this is the way we decided upon. This is the number of TID hours during a month. And so we just totaled up all the ones that had a month. And what we discovered was, in many years, it's quite the same, that there's a lot of activity in January, February, a lot of activity in November, December, not so much the rest of the year, except, and here's where we're different from Veronica's work, there's a midsummer spike. Doesn't show up in SuperDarn. Shows up like crazy with the spot data. If we put all the years together, well, here's 3 years at any rate, what we see is this same pattern that continues. So there's a lot in January, February, and then again in the end of the cold months there, and the cold months, and the cold months. But look at this. There's the midsummer spike. Where is it here? I guess in there, that's it. And then in this one, it's this one. But in the middle of the summer, something happens. No idea. So possible drivers, well, certainly from below, we could have anything having to do with the wind. So there's the polar vortex. This is from the Miro 2 models. The 60 north zonal winds go around by Canada. Gravity waves, which percolate up from the ground level. That's from the AIRS satellite. And then I took the winds in northwest, in the Midwest. I thought Kansas was windy, so I did Kansas, and now I'm doing all the other states out there. And then there's the volcanic blast, which I just think is wonderful. From above, you have solar flares. I showed you one of those. And space weather, AE max. We also had AE average and SIMH. And then we took time derivatives of most of these, thinking, well, maybe it's going along, it's really good. And it changes. We've got an acceleration, we write that down too. That didn't seem to do an awful lot. All right, so here's an example of the Tonga situation. This is an undersea volcano. Some years ago, it blew the top off the volcano, and so it was underneath the water. And then January 15th, 2022, that blew up. So it lofted this chunk of water up into the air. So it was about a mile wide, about a mile deep. It's a cubic mile of water, and it flung it into the stratosphere and then dispersed it. And that went around the world. Now, if you get water in the atmosphere, it generally rains out within a week or two. This, we get it in the stratosphere, it doesn't rain out for a whole year. This changed the models of the weather. They upped the number in front of that part. All right, so this is from various satellites. These different stripes here are different satellites looking down, and you can see the ripples going out in this big pond. This is a model, but taking those data and putting it into a model. The explosion went off at 4:30, 4:28 UT on that day. And I got interested in this in January because I heard it, it was the second anniversary of this big explosion. I thought, what the heck is that? So I started reading up on it. It's just incredible. So anyway, here's one of the models. And at this point, this is not 4 o'clock. It's by now 10 o'clock UT. And here the edge, right there, that's the edge of the blast wave. And it's halfway at that point between Hawaii and California, right? Halfway, interesting point. A little later, 13 UTC, the leading edge crossed the middle of North America, and land waves were detected at this time by the differential tech. So I was thinking, well, we should look about the United States, and I'll show you the United States version in a minute, clear wave. And I thought, well, could we get something a little earlier? How about East Pacific? Well, that would be when it crosses between Hawaii and California. So Bill here pulled the data for me for East Pacific, and it's mostly Rob Robinette listening to everybody who's telling them stuff from the United States. Thank you, Rob. So here's a map. This is California and New Mexico. There's Maui. These are the mid parts of their Great Circle roots. Here's Tonga. Tonga makes a blast. Blast goes up here, eventually crosses the midpoints. All right. Did anything happen when it crossed the midpoints? Oh, yes, it did. I'll show you that in a minute. Here's what it is. So here's time going along. This is California, and that's New Mexico. And so what I did is I made a big map. I laid a ruler on it, swung it around to see if there was anything that went through these two that lined up with Tonga. Yeah, it's this one, here and here. You draw a line from here to here, it points to Tonga. That was when the blast crossed those two places. Okay, you can use that to calculate a speed. Speed came out to be 355 meters per second in one case and 356 meters per second in the other case. I think that's fairly comparable. Does anybody know what that speed is? Anybody recognize it? Physics 1? That's the speed of sound. Yeah, there you go. So then we thought, well, how about not just Rob himself? How about the whole of the Pacific Ocean? And so this mainly turned out to be people from the East Pacific in any case. But there's, so this is the number of whisper reports versus the number of minutes since the explosion went off. And there's a big dip at 300 and also at 400. 300 minutes is when that blast hit the midpoint between Maui and California. Boom, there it is. Shows up with all the data. It doesn't have to be selected for you. And then at 400, it's when the blast hits the middle of the United States. There you go. This, I think it's really cool to see something we already knew about, but in this sort of new data pool, the ham spots. Here's somebody else's calculation of the speed. They got 318. All right, here's the wave when it got to the middle of the United States. Here's 13 UTC right here. It's coming along and it goes whoop, and then there's the wave. That's a TID caused by a ground source. All right, I think it's interesting to see it in different ways as well. So the one on the left there is pressure recordings from Chicago's O'Hare Airport. And this is right there when the wave came from Tonga up through the Pacific across California and got to Chicago. This over here is when it went from Tonga, the West Pacific, Asia, Europe, the Atlantic Ocean, and then came to Chicago. The thing went both ways. And in fact, with good equipment, it was seen going around the Earth both ways 4 times. It was the biggest blast ever, tied or surpassed Krakatoa. Amazing. Okay, and the other one, the one on the right, I thought was interesting. This is from the Welland Valley Radio Club in East England. And they had got bored during COVID and bought a whole bunch of pressure sensors and set them up all over their county. And so they were just there and they saw it. There it is when it came through England, coming across the Atlantic. All right, here's possible mechanism. Nobody really knows the mechanisms of these things. But at any rate, gravity waves, which we have a lot of at the surface of the Earth, can go up and then some distance above our head break as a surf breaks. And then sometimes, we don't know how, a new wave begins. It goes up, breaks again, and the tertiary wave would be the one that comes out into the ionosphere and makes a TID. Maybe. All right, so we looked at possible drivers of TIDs. So this is SIMH, space measurement, and the top version is just SIMH through a period of the whole year, and it just wobbles around like crazy. And then the bottom view is SIMH, but underlaid it with the blue histogram are the actual TIDs that we saw in our manual scanning of that data. Do they line up? Maybe. Here's another one, the polar vortex. Now, the polar vortex, you can tell just by the name, is going to be in the cold months. So that's January, February, and then November, December. So that works out pretty well. But look how low it goes in the middle of the summer, like nothing. And so that's certainly not going to help us with the midsummer spike. Not at all. Here's another one, the auroral electric jet. And it goes up and down quite a lot. Not so sure what it's really doing, but it's certainly not helping in the middle of the summer. That may help out in January, February, though. This one is the auroral electric jet change. And, well, no, but it's exciting to look at anyway. Here's another one, 60 north zonal winds, and then the 60 north zonal wind change. Neither one is doing much for you. So here's just the zonal wind itself. And particularly, it looks like it's good in the first January, February, but right here it's terrible. See, it goes down right when there's a huge amount of TIDs. And of course, that doesn't help at all. So, don't know about that one either. Here's the zonal wind change, nothing much there. Oh, sorry. I'm missing a picture. Oh, here's Kansas. Yeah, we got to go to Kansas. The Kansas winds, which you got from NOAA. And this one is the only one that has something intriguing happening in the middle of the summer. Okay. There it is there. It would be better if it happened before the TIDs. But at any rate, it's kind of the same sort of time. So I don't know. But at least it goes up in the middle of the summer. Of course, it's not windy in the winter or the summer there, so they think. Anyhow. All right, so here's the real conclusion one. So one of the things we thought to do is to look day by day really carefully at these various drivers. And so for every day of the year, we had the TIDs and their strength. Their strength we take as the number of hours for duration. So the TIDs and then the driver. And then we thought, well, what is it going to happen? The driver is going to have to somehow explain 30% of the days. All right. Well, we can't just give it its whole thing. So what we decided to do is give it its top 50%. So we took the top 50% of the driver and said, if you threw those 183 top values at the year, how many times would you hit when a TID happened? And that's a percentage. So each one got a percentage for each month of the year, and this is it. So, not really very conclusive. So the ones in January and February that were good were the polar vortex, the gravity waves as measured by the AIRS satellite. So those are the top two over there. Those top two red ones here. Sorts of funny stuff. And then the last couple are, again, the gravity waves from AIRS and the polar vortex. So those two things may well explain the end of the year, cold year stuff. And the middle is either gravity waves or the wind in Kansas. I don't know. I'm looking for more drivers here, folks. At any rate. So the conclusions are that LSTIDs in the cold months have several explanations. The polar vortex, the 60 north zonal wind does explain one of them. The 60 north zonal winds change also comes into it, and the AIRS gravity waves. But none of these are really stupendous. I mean, they could explain maybe 70%. Really? But that's better than nothing. And the midsummer spike has very few explanations at all. Winds in Kansas are the best. I still have to do all the other 49 states, though. I'm not doing Alaska. And no space weather driver seems to be important much at all. I don't know what's going on there. So for future work, we're going to look at multi-day sequences. So this is something that came out when we looked at the days day by day. The timing of the LSTIDs is not 30% randomly. It's nothing, nothing, nothing a week at a time. Nothing, nothing, nothing another week at a time. So these multi-day sequences we think are important. Then we're going to give some of them lag days. All right, so you didn't hit the day, but maybe hit the day before. Oh, we'll give you a point for that one then too. We have yet to do Europe, Australia, and the Atlantic Ocean. Lots of data on these places. We're going to do more years. We've done up to 22. We need to do 23. The whole solar cycle is coming into focus soon. We're going to look at longer period waves because this is from 1 to 4 hours. There's some at 5 hours, and I'm clear as what they're doing. Other drivers, if possible. We want to do automated detection of this, and so I exhort you to go see Bill Engelke's poster on how we're coming on automating the search for these things, because Veronica and I know it's tedious, right? There's references. You could read that online. Acknowledgements, everybody. And especially I want to thank you all for paying your taxes. A lot of this is national money. Thank you very much. Any questions?
Any questions?
Question over there.
What do you think the coupling is between acoustic pressure wave and refractive radio wave? Is it that higher pressure causes recombination to happen faster, and when it verifies, you have more information for electron density, the coupling?
I think that's quite a good possibility.
Or is there any nonlinearities in that?
And everything is nonlinear in the atmosphere, right? Yeah, that's why weather is so hard to predict. Right, yeah.
Thank you. No, I've got a completely naive question. I'm sorry for it, but you're mentioning pressure, acoustic pressure, physical pressure, rather than ionization. I mean, I'm familiar with, tropospheric ducting, for example, in VHF, which is, often seen between California and Hawaii, and you get the fog coming in. And this is a purely dielectric issue. It's not an ionization issue, at least to the best of my knowledge. Is that a there's something going on there possibly having to do with an atmospheric dielectric barrier rather than an ionization issue?
I don't think so.
Okay.
The electron density, there's a lot of literature out there that shows the electron density does change with the pressure, with the neutral atmospheric gravity waves. So the actual electron densities do fluctuate. Phil?
I could just make one other brief comment about that. The 100 kilometers is a very special place. That is the place where the electrons are still highly magnetized, right? So at 100 kilometers, the electrons are still highly magnetized. They're stuck to the field lines, but the ions are collisional enough with the neutrals that they can move off the field lines. I just moved a plus, and I left a minus behind, okay? Above that, both the electrons and the ions are magnetized, and now there's a different set of electrodynamics. Below that, everything's collisional, and it doesn't really honestly matter too much where the magnetic field is. The trouble is that you've got all of these waves that Mary Lou referred to, and she referred to the fact that they're coming up. The density is getting too low, they're breaking, and they're generating another set of waves. So you can think about that in an EE sense as a bunch of different filters. And the trouble is the filters are not stable. And yet for modeling, we don't know what that filtering effect is when you get things breaking at a primary level, creating a secondary level, breaking at a secondary level, creating a tertiary level, if that's really what happens. So this is right at the edge of modeling, too. So that's another reason why this is very nebulous, because, frankly, we're still all trying to work out the basic physics here. But it is near this very special place where the electrons are still magnetized, but the ions are not. And that's ion-neutral coupling.
I think we're going to transition to the last activity for today. Let's give Mary Lou, Dr. Mary Lou West, one more round of applause.